Hello, this is Terry Kuzma here at Penn State University, and today we would like to cover materials and nanotechnology. Specifically, we're going to go over an introduction to nanoparticle synthesis and some applications that are common. So this is an outline of the total presentation that we're going to look at. We'll probably break this into three parts. I took a look at it, and I think it's 75, 80 pages. So we'll try to get maybe 30 pages done in an outing and then continue to part two, part three, etc. So part one, we're going to go over a general overview. Then we're going to look at some common nanoparticle synthesis techniques, chemical reduction, and then attrition. And then probably starting on lecture number 2, we'll go over pyrolysis. I actually think pyrolysis is probably, in some senses, the most important nanoparticle method that we use. Mostly I would identify that because we get tons and tons of nanoparticles from the pyrolysis procedure. So it's valid because of its economic value. And then we'll go on to, that's a nice section, that's why I'm going to relegate it to a full lecture. And then what we're going to do is look at RF plasma, thermal decomposition, laser methods, and then some applications at the end of the presentation. So let's begin. So let's take a look at this nanomaterial synthesis approaches. And top-down approach starts with a bulk material and breaks it into smaller pieces using a mechanical, chemical, or other form of energy. In some applications, it could be described as the relative large amounts of energy to force materials into a specific configuration. So we can look at some examples of this, such as physical vapor deposition, shown as sputtering or e-gun evaporation. The bottom-up approach synthesis synthesizes the nanomaterials from atomic or molecular species via chemical reactions or a self-assembly driven reaction. This allows the precursor particles to grow in size or gradually assemble into the atomic or molecular precursors until the desired structure is achieved. That's rather difficult, so we generally get simpler structures from that method. And top down, we would use that method quite a bit for like thin films and to make more complex structures. So let's move ahead. The bottom-up approach we'll explore in this section includes pyrolysis, colloidal chemical methods, attrition. I got pyrolysis in there twice, RF plasma, and the pulse laser method. These approaches feature advantages and certainly disadvantages. There are trade-offs factors such as cost. Cost factors could include raw material, environmental factors, process symptom maintenance, and particle filtration. Again, the specific approach will dictate the size distribution, the environmental concerns, and the material type. So selecting an approach has many considerations that we'll have to look for a specific application. Examples we'll explore in this section include below. So both top-down and bottom-up can be performed in gas or liquid phases, supercritical fluids, the solid state, or in a partial vacuum. Key to both processes is the ability to be repeatable and predictable in the manufacturing of a nanoscale product. The process must control particle size, particle shape, size distribution, particle composition, and a degree of agglomeration. And agglomeration is defined as nanoparticles that would actually be driven by some type of energy to form a larger particle or a number of discrete nanoparticles going into a larger particle. Another important consideration is assuring a desired level of stability. Intuitively, nanomaterials have a reactive surface. That's why we like them. But we want to use this potential at the appropriate time. So often, nanomaterials are stabilized until the reaction is enabled. So let's take a look at some synthesis techniques. And the first one we're going to start with is the chemical reduction method. So chemical reduction methods have the potential to be scaled up even at room temperature. The chemical reduction of metal, that should be metal salts, is the most common method for synthesis of nanoparticles. Generally, this approach is very useful because it's easy and initially inexpensive. Naturally, liquid byproducts might be costly to dispose, and this method is applicable to a limited number of materials that could be done in this methodology. Chemical reduction methods might utilize both organic and inorganic reactants. Typically, a metal salt is reduced, leaving nanoparticles and evenly dispersed in a fluid. So this is typical nanoparticle that we might use for a bio application, just as a generic example. For things like gold or gold colloid, we might have a reducing agent such as sodium citrate or ascorbic acid, etc. And then we could, after we make the nanoparticle or during the process, what we want to do is have a secondary chemical reaction taking place so that we would actually cap the material and control its growth. So citrate is probably the most common material that we would use for that. And other materials that we could link to the surface to stabilize and to further chemical activity, we might place thiols on there. So thiols, for example, if we were looking at this material and assuming that it's a gold nanoparticle, thiols have a high affinity to actually adhere to the gold interface. So there's a thiol is defined as a sulfur head with a polymer tail. And what's nice about that, the polymer tail that would reside in this area right here, that polymer tail has the ability now to be conjugated to attach other biological agents. So that's a common theme. What we would do is start with our carrier material, like a gold nanoparticle, attach perhaps a thiol, and then that thiol, we could link other materials in there, like proteins, to direct this particle to a specific place, or other entities such as maybe sugars to make this particle invisible to the biological system. Might want to remove this particle from the system. So to make it stealthy, we might do something like attach a polyethyl glycol, etc. So that gives us the ability to do that. Of course, we can attach PEG directly to this material too. So aggregation is prevented by electrostatic repulsion or the introduction of a stabilizing reagent that coats the particle surfaces. So there's two basic methods. We would use the electrostatic one or a physical one, which we would refer to as steric repulsion. So several reducing agents such as ascorbic acid, citric acid, and their salts with this list. These polymers can include this polyvinyl pyridine, I can't pronounce that, organic ligands such as quaternary amines, thiols, and surfactants to help stabilize the nanoparticle. So particle ranges generally range from particle sizes range from 1 to 200 nanometers. And this is controlled by the initial concentration of the reactants and the action of the stabilizing reaction. So in our last example, we would grow our gold nanoparticle until the citrate would actually cap this outer core and then stop the growth of the nanoparticle from the salts. So example, let's take a look at gold. I guess this is the classic example. This is done in certainly many schools and certainly even at the high school level. So this is a nice method to show how gold nanoparticles are made. So a common method for preparing colloidal gold nanoparticles involves the combination of these materials, and you would get this reaction here that you can review. So again, here's a nice cartoon that shows us this process taking place. And it's nice, and we do this example all the time. And in fact, there's a lab linked to this lesson plan that shows the manufacturing of gold. So I can allow you to take a look at that lab exercise to further explain this. But as we're doing this reaction, you can actually see in the solution, you can see a visual indication of the size of the gold because it's going to change color. So that's very interesting. And again, this is common. Certainly we provide the lab examples I said before, but also you can view these in any number of places like on YouTube. So here's the formation of the gold nanoparticle. So we're going to have the growth of the nanoparticles from a seed, and we're going to have this isotropic growth, and then we could grow different materials in here. We could grow either spheres or nanorods. Spheres are the most popular, and what we're going to do is grow the seed crystal, and then this is going to grow a number of atoms until the citrate is going to be able to cap that surface and then maintain some stability at that level. What's nice is with these rules of chemistry, what we're able to do is get nanoparticles that have a nice sharp Gaussian distribution, that the particles are relatively the same size, and that's always usually that's very desirable for most applications. So another chemical reduction method that we could use beside gold is for molybdenum. So we can make these nanoparticles from the solution below that we could see. And one of the things noted in this recipe is that we're using materials like toluene. And that brings up, I guess, the idea or the concept or discussion that I guess an issue with these chemical reduction methods. What do you do with the waste products? And certainly you have to dispose of them in some way. And I guess the rhetorical question is, what does it cost you? So the cost comes at many levels. Certainly the financial cost to remove these materials and to store them safely, or to destroy these materials safely. And then the other cost is when we work with materials like toluene, that's a carcinogen, so we have to worry about employees and environmental impact. So I would say, if I was having a relative discussion about chemical methods, one of the things that would be of concern of mine is the environmental impact of these chemical solutions and the cost associated with that on many levels. Another chemical reduction method we could use, we can make iron nanoparticles. So these are used quite often as catalysts in many applications, and certainly to clean organic spills, etc. Iron nanoparticles are popular for that application. And again, towards the end of this presentation, we'll go over specific applications for nanoparticles. So another reduction method that we could look at in a popular nanoparticle is silver nanoparticles. So they're made in a solution similar to the gold nanoparticle, but I found this doing some research a number of years ago. This is a novel one where they actually grow the nanoparticles in between layered sheets, and actually the sheets help control the size of the nanoparticle. So I thought, if anything else, this isn't how people generally do things, at least not in my opinion. I thought this was a novel method, but I think it's good to review novel methods and take a look at that, maybe for some other ideas that you might have, or this is a template for some other manufacturing methods. But I don't think this is that popular, but I did think it was novel, so that's why I'm giving you the reference to the paper there and a description of this particular process. So let's take another look at another method that's popular, and it's attrition, and we would also call this mechanical milling of materials. So attrition, known as mechanical milling, is routinely used in powder metallurgy and mineral processing industries. In this method, mixtures of elemental or pre-alloyed powders are subjected to grinding under a protective atmosphere in systems that are capable of high energy compressive impact forces. Macro or micro scale particles are ground in a ball mill, a planetary ball mill, or other size reducing mechanism. The resulting particles are separated by filters and recovered. Particle sizes range from 10 to hundreds of nanometers. And certainly one of the things that I would, if somebody was discussing attrition with me, attrition is known to have a broad size distribution with varied particle geometry, because physically we're just making these particles. Once they're made, they can actually, the two small particles can be mechanically crushed back together to make a larger nanoparticle. So the size and the geometry and the distribution is rather large in attrition. That's why we count on filtration to narrow that Gaussian distribution for our particular application. So we could potentially get defects and impurities from the milling process, the media that's used to crush these particles together. And it's probably the number one thing when somebody walks up to me and says attrition to make nanoparticles, I would say that this is very energy intensive. So these generally take a long time to make, and they use quite a bit of energy. And again, just as a relative discussion of attrition, why would we use attrition? Probably because we can't make a particle in some other method. So this might be something that we would do when we're forced to do it, and certainly forced because this isn't that economically viable. It's very expensive. So you would only go to this when you couldn't create it by some other process that we're going to review within this notepad or other process that's available in industry. So attrition for single phase elemental powders or intermetallic compound powder is milled to the grain size and continues to decrease until we reach a desired level. And most of the time, these are in the nanometer range, 3 to 200 or something like that. So intermetallic compounds of the powder become amorphous beyond this point, below 3 to 25 nanometers, because the processes are low temperature. These newly formed grains tend to grow slowly. So mechanical attrition processes allow the preparation of alloys and composites that could preclude other manufacturing methods. High energy mechanical milling is an effective process for synthesizing metal ceramic composites. So this shows a picture of a rotary ball mill, and what we would have is our media that we want to make, shown here in the yellow. This system is going to rotate, and these are the balls that are in there, and what these do is mechanically smash into this powder and crush it together in hopefully the way we want to make it. So attrition rotary mills are likely to introduce impurities. This could serve as a sintering aid and may force eutectic liquids to initiate the sintering process. So surface defects from milling also might increase the surface defects and surface energy, which might be actually favorable for densification of a nanocomposite or to initiate the sintering process. So this is a popular method of making powdered metals, with each particle having a predicted alloy ratio. So what we're going to do is when we would break down these powders, what they're going to have is certainly a finite amount or balance or alloy constituent in each particle. But when they're very small, and if we would reassemble them randomly, what that's going to do is give us certainly a homogeneous alloy. And that's really important for materials so that they don't have local defect areas. So this is certainly a common methodology that people use in powdered metallurgy to assemble high precision steels, etc. So this is a picture here of CPM-3V powdered metal, and this is a proprietary product. I think the company's in New York that actually is the foundry that makes this powder, and they're used specifically for applications. Shown here is this knife, and here in the US, I guess you could potentially get a knife like this for a hunting application or for a kitchen. They might be $25 US, but I imagine that this Bark River knife, because it's a custom knife and uses this, they would call this a super steel, this CPM-3V steel. I would imagine that this knife is probably going to cost, an order of magnitude more. This knife might be $200 or $300. And why it's desirable is because that knife is going to stay sharp, because the alloy is very homogeneous, and we controlled the nucleation of these particles, and the heat treatment is very uniform across the system. So we're able to get this steel to stay amazingly sharp over long periods of time. So it makes this knife super duper durable. So not only in applications for, this novel application for this particular knife, for campers or hunters or whatever, but we could use the same application for steel parts that see high stress, for cutters, for industrial applications, that we would use cutter wheels or drills or something like that, drill bits. So this is a really good application of that, and how the manufacture of these powdered materials through attrition can be reassembled into other networks to give us particularly desirable items. So this is, again, examples of attrition. Different materials that we could get from attrition, the typical grain size that people might have a desire to make, and then importantly here, it gives us the time that the attrition process takes place. So I think that it's amazing that the attrition time, like for that iron aluminum alloy at the bottom, is going to take 4 days. And then if you would look at the iron carbide ahead of that, the one listed above that, that's going to take 500 hours. And 500 hours is just, certainly a long time. But the thing that I'm thinking about in that long time is you're going to have to power up the system for 500 hours. So in the end, all this particular material or that powder that you're making in 500 hours is going to be relatively expensive, because it took a lot of energy to manufacture this particular product. So again, I'd like to stop at this point. Lecture number 2, what we're going to do is we're going to concentrate on pyrolysis. I think that's probably one of the most important, at least financially, globally, one of the most important nanomaterials, discrete nano particles that are manufactured, like for the paint, rubber industry, etc. So what we're going to do is relegate that to some more detail, and we're going to have our own presentation on that. So that'll be part 2. So thanks for viewing this presentation, and I look forward to talking to you the next time when we review pyrolysis. Take care.